Okay, welcome back everyone to What's a Microcontroller with Python and the Microbit. This is day 3 of 3 in the workshop. So on Wednesday, the previous workshop, we did a lot with lights, but didn't quite make it to push buttons. And we talked about most of the concepts that are covered in those activities. And additionally, we talked about some of the measurements and unit stuff that was planned for Monday. So today, I'd like to start out with just a few quick examples from push buttons, and then experiment with the servo a little bit and the potentiometer. That's the twistable knob that we added to our breadboard. We'll also talk about some of the activities and projects that are that are planned but have not yet been published, and then we'll round it out with teaching materials, parallax from cyber.org. And I'll also do a quick little demo of some of the robots that Parallax has that also use the microbit. So this was the homework, was to build up the circuit so that it looked like this, with the exception that, so that it looks like this. So the LED lights and the push buttons were already on, and what we added were the battery pack. And it was just pointed out to me, I think by Cheryl, that my lead colors are backwards here. I need to correct that. Thank you very much for mentioning it. And so we also added the potentiometer and this servo, which is a motor that turns to and holds certain positions depending on the signal the microbit sends to it.
Can you share your screen?
Oh, goodness, I did it again. Thank you. Let's see here, share. All right, there we go. Okay, so I almost want to start this over. Welcome back, everyone, to the workshop. And here's a visual of what I was talking about in terms of what we did and what we'll do today. Here is the potentiometer, the battery pack, and the servo, which you all added during the homework. And so today we're going to start off with the push button circuit. And I just want to, we already have them built, so we can skip to script and tests. So here is a test for the push button connected to P6. By the way, you guys had a chance to build the servo and connect the battery pack according to the instructions. I know that some of you are in need of a little bit of troubleshooting help, but overall, how do you like the little red check marks as a way to point out action items? Everybody okay with that? All righty. There, now we've got everybody. Okay, so let us test out the first push button and make sure that it's working for everyone.
Andy, do we need to hook our battery packs back up then too?
Not for the push button. I'll give you a yell when it's time to connect the battery back up. And thanks for disconnecting it, because it will drain your batteries if you leave it connected. So when we need the battery, which is just for servo motors, or if you're going to disconnect from your computer and do a project remotely. So, all right, so we have the code right here. And so let's all go back to the python.microbit.org editor. I'll paste that into your chat as well. There we go. So go ahead and open the python.microbit.org editor. Paste in your code, hit connect, and then flash. And this particular activity is using the serial terminal. So after you've flashed your code, click the Open Serial button, and it will scroll down with repeated measurements of the state of your push button. Mine is currently in a state of 0. And how are we doing with that? All right.
Is ours supposed to look like yours?
Yes, yes. We want to see a, while you're not pressing on the push button, we want to see the state reported as 0.
Okay.
And so do you have, are you seeing 1 instead?
No, it's just spelling out letters like ATETAS equals. I'm going to look at the diagram again. Maybe I have something wrong.
Well, no, actually that's because it sounds like it's trying to spell it out, but it's, go ahead and just hit close serial.
I got it. I was connected to the
Cyberscope.
Yeah, also at the same time. So I forgot to disconnect from that.
Okay. Yeah, and so that's one of the reasons why the instructions in the textbook, that doesn't happen to everybody, but I was concerned that it would happen to some of you. So I did my best in all the instructions to always say, in the written instructions, not necessarily right now, but in the written instructions, I try to say, all right, hit disconnect on the Cyberscope, go to the python.microbit.org editor and hit connect. Now, the P6 push button should be the lower of the two. And when you press and hold on the button, if your button is wired correctly, you will start seeing state equals 1. And then when you release it, you'll see state equals 0. So we want to make sure of that. And in general, if you see state, if it's stuck at either state equals 0 or state equals 1, that normally means that there was some kind of wiring mistake. And so this is a partially a test to give us a heads up. Hey, there's a wiring mistake. We want to troubleshoot that before moving on and trying to use the push button to say control the brightness of a light or the position of a servo. So how are we doing? Has everybody got 1s when they press and hold the button and then 0? All right. Oh, I see a no though. Jennifer, can I help you? No?
No, I'll figure it out.
Okay. Let's see here. I don't know. I'm kind of uncomfortable with leaving you behind, Jennifer. What if we, no, actually I wasn't since push button presses. So just very quickly, I'll paste you the link of the push button wiring. Let's see here. Okay, so that is not the one that we want. This looks good. So the parts section in the page I'm about to paste into the chat. Okay. So the push button does have fairly detailed how it works, which basically talks about the fact that when you've got this 3-volt connection on one of the push buttons terminals up here. And when you're not pressing the push button, that 3 volts is not connected to the rest of the circuit. All the rest of the circuit sees is ground because P6 is listening. It does not supply any current. It just watches what's going on with the circuit. And the rest of the circuit sees ground if you were to put your voltmeter on it, which would be a little bit too time consuming for the hour and a half. But once you press the push button, this portion of the circuit sees 3.3 volts instead of ground. And so when P6 sees 3.3 volts, it stores a 1 in a piece of memory that stores what the IO pin reads. And then when the button is not pressed, 0 volts is applied to P6 and it stores 0 instead. And so when we're looking at state equals, it's either going to be 1 or 0. And then we have that print statement. And by the way, I added some questions for the students to go through to basically direct their attention to various parts of this diagram, because there is a lot here and there's a lot to think about. And so that's why we added these questions. And then the answers are in the teacher's guide for you to talk about with the students. And I want to remove that parentheses at some point. Okay, so at any rate, so once you've got this tested, the next thing we want to do is test the second push button. And I have this wired up differently from the way you have it wired up. And then in one of the later activities, or no, pardon me, I'm sorry. What we do, what the lessons do is they wire up the P9 push button initially so that its resting state is 1 instead of 0. And we do that by, instead of plugging the resistor into the lower leg like we did on the first one, we plug it into the upper leg. And so its resting state is 1. But the way we built it, just to kind of try to have some fun today, is comes after that, where now that that connection between the IO pin P9 and the push button is going to its lower leg on the breadboard. And so so then there's a script and test to test I believe both push buttons. So I'll paste that to you next. All right, so let's try this out in the editor. You'll need to close serial, select all, and paste over it. And you can, of course, optionally save your work as well by updating the script name, load save, download project hex, and then you'll have it for later. So when we flash this and take a look at it in the serial terminal, now you can press and hold 6 and you'll see state 6 is changing to 1. Release the lower push button, press it, release it, and the state shows 1 when it's pressed and 0 when it's not pressed. And then the upper push button is connected to P9. And so the variable state 9 will hold either a 0 or 1 as you press or release it. This is also kind of a nice thing to reinforce the idea of binary zeros and ones as used in computing and electronics. All right, how are we doing? Good, I'm getting some thumbs up. Thank you, Sarah. Edward, you okay? Good, good. Michelle? Brian? All right. And for the umpteenth time, feel free to just speak up and say, hold up, I need some time, or I have a question. So being able to read 2 push buttons is great. And there's also 2 push buttons built into the microbit that are in a separate set of lessons that go with the microbit itself that I mentioned on day 1. Now, so there are some things that are done with push buttons after you've connected and tested them. Now they can be used to control other things. And so one example would be, we're measuring the control on an oscilloscope here. That wasn't where I meant to go because I want to skip a few things to save time. Okay, so let's see here. Huh. Okay, it's because I think I put some of the push button control stuff in two button control. Okay, here we go. So this is so there's one button control in the build and test a push button down in the your turn. So this is another your turn where it was kind of a jump. So I added some code that they can copy as opposed to so here is an interesting change that the students can make that allows us to say, hey, look what you can do with a variable that stores a value. So we're going to comment out the print and the sleep, and then add this one statement, pin 13.write digital of state. So state receives its value from pin 6 read digital. That's either 1 or 0, depending on pressed or not pressed. And then pin 13.write digital can receive a 1 to turn the light connected to P13 on, or a 0 to turn the light connected to P13 off. And so it's, again, reinforcing those binary values. So let's do that. Need to go back to my previous program here. Sorry. Okay, so we're going to comment the print statement and the sleep statement by inserting a hashtag or #, depending on your generation, to the left of it. And then say pin 13.write digital of state, which we've done stuff like that, but it was with 1 or 0 in the light tutorials. And so now, again, we're taking a variable and doing that. And so when you run this, what we want to see.
Will you paste it in the chat?
Oh, I'm sorry. Yes. There we go. There you are. So let me know when you've run that. So basically, when I'm not pressing the lower of the two push buttons, all the lights are off. And then when I press and hold it, the green light comes on because it's mirroring the state of the lower push button. Okay, everybody got that? Okay, looks like some of you are still working on it. I'm going to change the code to do something similar to what we did in the your turn section. Okay, so the your turn section in that I just hand entered what something similar to what's in there, and I'll paste that into the chat next. Okay, so go ahead and try that piece of code. And hopefully when you press and hold the button, it should blink slowly. And you'll need to press and hold it for long enough for it to blink. All right, so does everybody have that working? Excelente. And so the idea is that you can do it with two push buttons and control two blinking lights. And you can even, actually one that's kind of fun. Let me see if I can find it for you. I think two push button control is kind of neat. Let me download this real quick and then put it in the editor and make sure it's the right one. Yes. Okay, so let's try this one. This is kind of at the end of the push button lessons. I'm trying to cover a lot of ground, so we're skipping some things. And my hope is that you'll be okay with going through it more carefully, or if you want to have a follow-up meeting with me to talk about any of this, I'll be glad to do that. So here is a program near the end of the chapter where you can press and hold the one button to make the light pattern rotate upwards and another button to make it rotate downwards. And it puts together some of the things that we introduced earlier, like there was an introduction to lists on Wednesday, and here we have a couple of lists, a list of pins to access and a list of times that they stay on. And then the rest of the script uses those concepts to show in an application how lists can be used to get an interesting effect without having a huge amount of code. So if I stop share, I forgot to flash it. All right, so now if I press the upper of the two push buttons, you can see hopefully that the sequence of lights goes upward. And then if I press the lower of the two push buttons, the sequence of lights goes downward. And so, oh, Jennifer, I'm glad you found the wiring error and that now it's working. Thanks for the chat. All right, folks. So let me know when it's okay to move on. I want to make sure that you can all sequence the lights like this by having them rotate upwards and downwards. Excellent, thank you.
So what if your red light's not flashing? The green and yellow are, but the red one's not.
Okay, so that might mean that there's a circuit error somewhere. What I would do is I would check, especially the ends of each. So for example, here I have the same symptom because this end of the resistor is floating. Now, if it's connected into a different row from the LED light, that would also be the case. But once you get it into the same row as the LED light, as the red LED light, then it will start to flash. Another common circuit error is just to have the shorter pin and longer pin reversed from the other LEDs. You want the longer pin on the left side of the valley and the breadboard, and then the shorter end on the right side.
My resistor just wasn't pushed in good.
Okay, yeah, that's very common. And your students will inevitably ask you about that. And so sometimes I've heard from teachers, some of them, that they actually give their students a printout and a Sharpie so that they can go through and actually Sharpie over every part that they've checked. And that has been helpful for some students who have a ways to go on the attention to detail side of it. I was one of those once upon a time. Okay, so next up is so I'm going to skip over the measuring the LED light with an oscilloscope. That the only thing I want to say is that it's similar to what we did with the blinking light yesterday, except for that you have two different colored graphs going on. So it's graphing the push button, and notice that both the push button and the LED light are low, and that the program that was running here was just to press and hold the lower button and see the green light blink. But we added in the Cyberscope measurement, and as soon as you press and hold the push button, the graph of the push button goes up, but at the same time, the light starts blinking, and we can see that graphed here in the red trace that's going rapidly up and down. And then there's some more oscilloscope operation things like just briefly pressing and holding the push button to trigger a number of LED on-offs by modifying the code slightly. And then
Excuse me a second. Do you want to be sharing your screen? Is that
I
possible?
do. I did it again, didn't I? Oh, goodness, sorry. All right, share screen. Number 2. There we are. Okay, so so the idea here is that we use the probes and we go ahead and connect one probe, the black probe, to the push button, and then the red probe to the green LED. After connecting the probes, download this and load it into the Python editor, use that to load it into the microbit, then switch over to the Cyberscope, hit connect here, and both of the traces will be low. We'll be sitting here at 0 until you start pressing and holding the push button. When you press and hold the push button, the black trace will go high up to 3.3 volts. And the program, the script has it so that while the push button is held down, the light blinks, just like we did earlier. And so you can actually see the graph of the light blinking while the push button is held down. Additionally, the program can be modified so that you just press the button briefly, but it still initiates a sequence of several blinks. And you can see that in the graph. And if you're running the program, you can also see that in your lights behavior. This, by the way, is the foundation for electronic communication between multiple devices. So it's one of the reasons I have it here. And I do mention that in the lesson. Then there's triggering, which we did yesterday. We hit the trigger and set it to rise, and then set it to, well, channel 0, which is the default. And then note that even though the graph is now at an angle instead of straight up and down like it was with the blinking light when we set the trigger, notice that the graph does adjust itself so that it intersects with this vertical purple line and the horizontal turquoise line. And so those are and then, you know, we experiment with moving the trigger over and setting it to fall and seeing what happens, and just starting to get familiar with how an oscilloscope can line up you know, its information with a particular event, like when the line falls down and crosses that intersection of those two crosshairs. And then, as with everything else, we have our review and practice and solutions. And then there's more for you, which we will be talking about soon with assessment materials. And so that's a very kind of topical treatment of the push buttons. There's much more inside the tutorials. Next up is Servo Control. And for homework, we went up through connect and test the servo and script and tests, right? Is that right? Okay, so how's everybody doing? I got one report of a servo that wasn't quite doing what was expected of it. Let's look at what was expected of it first, I guess. So here we are in connect and test the servo. And so, well, I mean, first for the homework, we found the battery and connected it, and then used the voltmeter to measure the battery's voltage. And typically that's going to be around 3.1 volts for new batteries, maybe even 3.2. Does anybody remember their numbers?
I think mine was 3.29.
Oh, wow. Okay. That's those are some fresh batteries. The batteries are usually well, they're supposed to be 1.5 volts, these alkaline batteries, but when they're brand new, they're actually around 1.6. And by the time they're dead, they're usually, at least for our purposes, 1.4, 1.3, something like that. And then since the batteries in the pack are connected end to end, the 1.6 plus 1.6 would be 3.2. And so I guess these batteries are kind of in the middle of their useful life at 3.1. 3.0, I guess, would be 1.5 volts exactly. So no, actually, yeah, 3.55. So they're on the newer side. Let's see here. There's lots of informational stuff again for the students to read through and then answer questions on. And then we get to connect the servo. Okay, so here is the servo. A servo is a device that turns an armature called a horn to various positions, and it actually turns to and holds those positions. A servo is a device you'll find on model airplanes to move those airplane flaps around as the airplane is flying. Model boats and cars also have them, you know, for steering purposes. And so the airplane flap or the boat rudder would be attached to the servo horn, and the servo would turn that horn to certain positions as you're driving the vehicle with a radio controller of some sort. Let's see, and it's got a cable and a plug and little flanges and holes to attach it to some part of your radio controlled vehicle. Well, it works great for other things like animatronics. So in school plays, if you want something to move, sometimes a servo is going to, or in Halloween demonstrations, if you want something to move automatically, you can use a microbit and a servo for that. And one of the things that we do, because part of the lesson is a little bit about angles and angular measurements. So one of the things we do, I am screen sharing, right? Okay, good. Thank you. Is we basically first turn the servo all the way. There's little mechanical stoppers inside the servo. And so you want to put on the horn and then turn the horn all the way clockwise until it hits the mechanical stopper. Then we don't know where it's going to be at that point, but once it hits the mechanical stopper in the clockwise direction, you pull it off and then put it back on so that it's just a little bit below 0 degrees, or, you know, horizontal pointing right. Once you've done that, you're ready to start building the circuit to connect the servo. So here we did that, and then plug the servo in, and then reconnected the battery pack. And at that point, I think I went by that a little bit too fast. So, and then reconnected the battery pack so that your setup overall looks like this. Now we have a potentiometer here, but we haven't gotten there yet in the actual textbook. So this is ready to go parts wise. So now we want to run a script to make sure that it's turning to those, now we want to run a script to make sure that the servo can point its armature at roughly 0 degrees, roughly 45 degrees, roughly 90, and roughly 180. You know, it might be, you know, it might be a little shy of those, and maybe by the time it's 180, it's here, but in general, it's going to be somewhere in the neighborhood of those angles. Copy.
Can I ask a question about your drawing?
Yes. Which
Okay,
one?
I feel
This one?
silly about this. No, I'm sorry, the one with the microbit.
Okay.
A little higher. Oh, maybe it was on the previous page.
Yeah. One of these.
Yeah, but can you hold on for just a minute until that one, stay right there.
Yeah.
So
Okay.
it makes sense to me when I plug the battery pack into the, well, I guess it's to the IO adapter. It makes sense to me that the red would be on the red side and the black would be on the blue channel. But
Yeah, I
and it
think
does slide in
Cheryl
that way,
pointed
but
this
you're-
out also. Okay, so yeah, I made a mistake here and I have to go through and fix quite a few drawings, I think, because I
okay.
made a mistake here.
Okay, because I struggled with my battery and I couldn't figure out why, and I wanted to put the red on the left and the black, and it fit that way, but I still never got the battery.
Yes, thank you to both you and Cheryl for pointing that out. I will get on that. What happened is that the first incarnation of the adapter actually did have its wires this way. And when I updated the drawing of the adapter, I forgot to update the drawing of the,
Okay, thank you.
yeah.
You should have seen me trying to get the plug in there that
Oh,
way
you
from the
guys,
picture
I'm so
last night.
sorry. Yeah, I need to fix that quickly. All right. So, so once we run the script, we want it to do this. Provided that you have your servo plugged in the correct, or your battery pack plugged in correctly, not like I showed it in the picture. Let's see here, chat. Paste. Okay, there is the test code. Okay, so now we have, this is the starting position, 0 degrees, 45 degrees, 90 degrees, 180.
Did you want to share your screen again?
Okay, so I'm not visible to you. I guess I should pin myself. Let me see if I can. Oh, am I visible or no?
I guess you are. It's not full screen, but I guess I can see your hands and I can see the device.
Okay, yeah. So it's just about to restart. So there it is at 0. 45. 90. And then 180. So that is the overall result we're looking for. And incidentally, I mentioned when we're not going super fast and following along with the instructions, it makes more sense. But basically, the when I talked about removing the servo horn, that's without the servo connected. So here the servo is disconnected, and I'll turn it all the way until it reaches a mechanical stopper that's inside it in the clockwise direction. There's also one in the counterclockwise direction. So assuming that I had my horn, the servo horn on kind of a random spot, turn it all the way counterclockwise, remove it, and then put it on just about a notch or two below what would be 0 degrees. So 0 degrees would be straight to the right. And this is just, so 0 degrees would be roughly there. And then the stopper is a little bit below 0 degrees. And then when you push it back around, the stopper will be a little bit beyond 180 degrees. And so that's a first step before connecting and running this program. And then once you do it, then it will show 0 degrees, 45, 90, and so on. Okay, so Jennifer, your servo is being blotted out. If you put it maybe in front of your person, there we go. Okay, now it's looking good, but it's not moving. Oh, there it is. Okay, perfect. And that looks like, yeah, there we go. Back to 0. Beautiful. Okay. Everybody else good? Nope. Okay. Nancy, how can we help you?
Well, so I tried to reset it, but like mine won't move.
Okay.
Like when you had it, you moved it back another 180 degrees after you set it. Mine will not move.
Interesting.
It's
So
like-
your servo is just mechanically stuck. It won't go. Okay, so make sure to unplug it from the breadboard while you're doing
It
this.
is.
Okay.
is.
And so even though it's unplugged, it seems like it's mechanically stuck.
Yes.
Okay. We will have to send you a new servo potentially. Because yeah, it should move fairly easily. I mean, as you can see, I'm just using one finger
Right.
to move the
Yeah,
servo.
mine
around.
never really did that. I mean, yeah. No, it just doesn't want to do that. And then this last time I tried it while you were setting yours up, it started to spin again where it just didn't do anything. It's just vibrating on the desk. So,
Okay. Now, your battery pack is for sure connected.
yes.
Okay. And so it's just, yeah, go ahead and unplug your servo. And I do apologize that our servo activities, just watch and we'll send you a new servo. If you could, well, actually I can just write it down. Okay, so that is Nancy. Okay, so we will send you a new servo, and sorry about that. Defective servos are not common, but they're also not 0, as we just saw. All right. So now's my cue to remember to reshare the screen. There we go. Okay. So once you've got the servo connected and tested, we already have push buttons. So why not use the push buttons to control the position of the servo? And I've skipped over a number of things about, I may want to back up, but let's just have some fun for a few minutes. And so we'll do the push button servo control. And then hopefully there'll still be time to backtrack and talk about some of this. Chat. Will you talk about the difference between continuous rotation and standard servos from Corey, I believe? That's a good question. Okay, so a standard servo is the one I described that goes into, see, I'm screen sharing. So a standard servo is like the one I described that goes into airplane flaps and whatnot, but we also have continuous rotation servos like this one right here. So behind those wheels on that robot are continuous rotation servos. So the way it's rolling there and avoiding stuff is an example of continuous rotation servos. And with the microbit, this is kind of a fun one. The microbits have radios in them. And so there's one microbit with a radio connected to the computer. So that's right here. And the script has its radio running and broadcasting. So all these robots also have microbits in them. And so they, of course, have the continuous rotation servos. And so this is from the Cyberbot lessons, and it's getting ready for the cybersecurity lessons, because we're using an open form of communication where anybody can see what this guy's broadcasting. And so when Ken types in the instruction of the terminal, all of the classroom's Cyberbot robots will perform whatever maneuver he typed into his terminal, because it goes from his computer to that one it goes from his computer to that one microbit that's connected to his computer with USB. From that one microbit, it gets broadcast over radio so that all the rest of the microbits receive it, and then their scripts are listening for instructions on where to make the robot wheels turn. Thought you might enjoy that as an example of another thing you can do with microbits in a different platform. Okay. Back to push button servo control. So we already have the circuit. And did I already? Yeah, servo buttons control. I already pasted that in. So I just need to catch up with you guys. I'm assuming you guys are already holding the push button and moving your servo back and forth. Is that right? I'm getting some nods. Okay. Flash. Okay, can you guys see my my screen? Or rather, can you see my my board? All right, so now I'll go ahead and press and hold one of the push buttons and nothing's happening. I'm pressing and holding the other one and nothing's happening. I wonder what I did wrong. There we go. So I'm pressing the lower button and then I'm pressing the upper button. So the lower button makes it go clockwise and the upper button makes it go counterclockwise. So now we're starting to put things together from previous chapters. And one that's really fun, I think, is tilt servo control. Now there's an entire chapter on tilt and it goes pretty deeply into the physics of it. But in this example, basically, if you hold your servo to your board, oh, I need to get back to screen share. So here's an example where if you hold the servo next to your board, just like it's shown, there's an accelerometer inside the microbit that can tell you at what angle you have rotated it. And so by measuring the rotation angle of the accelerometer, the script can say, okay, well, hey, servo that's being held against the board, keep on pointing up. Or you can just hold the servo still and then rotate this board like a steering wheel and it will control the servo horn. So this is a fun one. And here is the script. Paste.
I'm getting a line 24 error.
Okay. Line 24. I don't have a line 24. You may have pasted in, but not over the entire program. Try shading, because I only go up to line 22. So try Control A to shade your entire program in the editor, and then Control V to paste over the whole thing. And then reflash and see if that gives you a better result.
I'm good.
Okay, excellent. By the way, see, can you guys see me, or can you see my board? Okay, so I'm going to hold the board up and down, because that's what you need to do, is hold it like you're holding a steering wheel. And as I rotate the board, hopefully you can see the servo pointing in a direction that follows the board. And the idea is, if you hold it next to the board like this, see how it tries to continue pointing up. So like the robots with the radios, this is another example of one of the cool sensors that's built into the microbit that you can use to enhance. You know, it depends on which way you look at it. We can enhance the fact that the microbit has cool sensors with a servo, or we can say, oh, all the things that we can do with servos are enhanced by the ability to sense the rotation. And notice also that the microbit is using its clock second hand on its LED matrix display to also try to point up on the display. Okay, so how about that? All right. So let's see here. Oh, measuring servo signals. Okay, so my computer always crashes with this one when I'm trying to present, so I might not run it, but the last time everybody else got it to work. So let's give this a try. So one of the things we talk about at the beginning or earlier on, let's rewind for a second to how servos work. I think I might need to be sharing my screen. All right, here we go. So in the connect and test the servo, under how it works, we have something still that says, all right, if you say pin 16 dot right analog of 26, the result of that statement is 0 degrees. If you say pin 16 right analog of 51, the result of that is 45 degrees. And then, you know, larger numbers, 77 gives you 90, 180 gives you 128. And so it's left to the students to, you know, verify that something halfway between 77 and 128 will give them 135. And we also talk about the on-off signal. So we've had a chance with the Cyberscope to measure on-off signals already and graph them. And part of that in the earlier chapters was preparing for this idea that, okay, well, now the on-off signals are happening too fast for us to see. They're coming at 50 times a second, actually. because 20 milliseconds or 20 thousandths of a second, if you go through the math, it turns out that 50 of those are delivered in a second. And that's what it takes to make a servo maintain its position or speed and direction if it's continuous rotation. And so the idea here is to connect that the number 26 gives us 0.5 millisecond pulses, and that gave us 0 degrees. And then all the way over on the other end, once we get to the number 128, that gives us 2.5 millisecond pulses to the servo and to make it turn to 180 degrees. Now, these numbers don't really seem very related to each other, do they? To me, I don't like that. It doesn't really give me a happy feeling. But what it does do is it gives us an opportunity to use y equals mx plus b to say, all right, if I want thus and such an angle, what magic number do I need here in the servo statement? And so that's what comes up in equations for setting servo angles. So basically, this activity of, well, gee, we have these numbers and they're somehow related to servo angles, sets us up for a lesson in 2 equations and 2 unknowns, and how to figure out what to multiply by and what to add in order to say, well, hey, if I, want a particular angle, what magic number do I need to give to the servo to make the right signal to make the servo turn to the right position? And so this goes through the y equals mx plus b solution. And then, of course, we have the students practice that. And then we even have the students implement it in a script so that they can type in a value and see what angle it's going to turn to. And then they can also type in an angle and see what value they need to make the servo turn to that angle.
So Andy, they're, hold on, I had a question.
Yeah.
So they're writing a JavaScript or no Python program to figure that out, correct?
Correct. Yes.
Got it.
Well, they're doing it on paper first. And then we're having them apply that on paper part to write the script. Yes. Yeah. So we're taking the results. Yeah. Excellent. Okay. Let's see here. Got just a couple more minutes, and then we're going to talk about the some of the teacher materials. So let's go back now that we've talked about how those signals work. The end of the chapter is actually measuring those signals. So I'm going to send you this, and this will be a thing where we're going to go to this page, and we're going to have to right-click servoplot.hex and do the save link as, and save it in our downloads. And then we'll go and I'm going to do this just for you once, and then we'll do it together. So then you open it with your Cyberscope and flash it. Then remember to hit disconnect. Then we'll go to cyberscope.parallax.com. And this will be important. Before we connect, we're going to choose oscilloscope. And then go way down to 5 milliseconds per division. And then set the trigger to rise. And we'll need to also set our probes on the, need to show you how to set up the probes. Okay, so we need to set up the probes like this, where P2 is connected to the P16 row where the servo is. So let's all go ahead and do that. Everybody got that? So we're going to clip on to the 3-pin header that's at P2. It's the third row up. And then we'll plug the other end, the jumper wire connected to the other alligator clip, into the same row as P16, where the resistor is connected to the servo. Okay, everybody got that? All right, so again, now I'll paste you the link. Okay, so servoplot.hex. Be careful, because I want you to go exactly with me on this. So let's see here. So first I'll paste you the link to the page. There we go. Oh, that's too, I sent that as a direct message by accident. And after this, we're going to break and talk about the teaching materials for this. So go to this page that I pasted in to the chat, right-click servoplot.hex, select Save Link As, and download it. Then go to the python.microbit.org editor and drag and drop the servoplot.hex file into the editor. Connect and download, or connect and flash rather. Then disconnect. Over at Cyberscope, do not hit connect yet. Cyberscope should look something like this. And when you get to Cyberscope, the device drop down is set to auto. And we're going to change it to oscilloscope. And then set the time per division to 5 milliseconds. We'll also set the volts per division to 0.75 milliseconds. Not hitting connect yet. Yeah, it won't let me do that yet. Okay, so once you've got to that point, with your device set to oscilloscope, your time per division set to 5 milliseconds, and your volts per division set to 0.75 milliseconds, then, and I need to turn off my camera for this in hopes that it won't crash my computer. Mute video. Okay. So your servo should be turning in to those same angles it was turning before. So when we hit connect, we should start seeing some signals, and I am not, unfortunately. What did I do wrong? Okay, does anybody have this on their display? Nope. Okay. Because we're running short on time, I'm gonna discontinue this. Sorry, everybody. I really want you to see what Nicole Litterer has been doing for your teacher materials. It's some really great work. So let's put this on hold and maybe come back to it. Okay, so stop share. All right. So Nicole, are you with us?
I am here.
Hello, Nicole.
Hi.
So a quick intro of Nicole. She's an Iowa native, currently working as the Director of Curriculum and Technology Support for the Anamosa School District in her home state. She has master's degrees in teaching and learning and educational leadership, and is now working on her doctorate with a focus on continuous improvement models at the University of Iowa. Now, since 2015, Nicole has also been working with Parallax, as if she doesn't have anything else to do, right, Nicole?
Right.
I don't know how you do it. Anyway, she's been working with Parallax on our various educational projects and products. And so she's been the one who's been writing the accompanying assessment materials, standards, alignments, teachers' guides, and other things. And so she's going to show you what she's working on for this set of lessons that we've been going through. All right, take it away, Nicole.
All right. Thank you, Andy, for that nice introduction. And hello, everyone. Okay, so it's a Friday. I will talk quickly. Everyone probably has things they want to do, although I don't know what time it is there. It's 14 here. So anyway, move this Zoom thing out of my way. From here. Okay, so I have 4 documents to show you today. The first is the teacher's guide, and I'll use the electrical measurement one for each one that I'll talk about. And so the teacher's guide has the standards in it, and I have pulled standards from a variety of different places. So as you scroll through, you can see which ones are here. But I started with the K-12 computer science framework, and I included middle school and high school, and the ones that are pertinent to the electrical measurement or whichever module you're on. And then K-12 computer science standards, our California Career Technical Education Model Curriculum Standards are here. And then I'll keep going, and the ISTE standards. You'll see them in here as well. And then also in each teacher's guide, you're going to see a short summary of what is in the module. And then if there's any background or technical information that you might need to help you or your students be more successful with it, I have included that here as well. Then there's some tips on teaching the tutorial, more instructional practices, things like that. There's some suggestions for differentiation, or if you have some students who need some extensions, there's some suggestions here for that as well. All of the activity outcomes for each module are here in one place. So that's kind of a nice place to know where you're going, what outcomes are for students. They're all here in one place. And then the student self-checks are here. Those come at the end of each activity. So students can come back and do a self-check of their own learning. So those are also here for you. And then any vocabulary. that is in the tutorial is found at the end here. So that is here. And then there's some references to some of those documents that I used. So that is the teacher's guide. And then you've seen in each of the activities, or most of them anyway, embedded in the lessons, there's sometimes your turn activities. And so we have the answers to those, kind of the teacher's answer key. So what you're looking for is a your turn and then the name of the module. So I can just go through and then all the answers are there for the teacher. And then we have a couple of different ways that you can do some practice exercises or some different types of assessments if you want to. So embedded in at the final lesson of the module are some questions, some exercises, and some problems. So these are, I guess I would call them mirror problems. So I've made two problems that are very similar, two questions that are very similar. One of them you'll see on the website, the other one is here. And I have split them apart so that oh, this one is not split apart. I need to do that. Shame on me. I had them split apart so that the questions were all on one page and then the answers were down below, but it looks like I didn't get that done on this one. So I'll get that done for you. That way, if you're trying to copy it, you just want to make a quick copy of the page. For kids, you don't have to pull apart those two pieces. So anyway, those are question banks if you want to do just some summative assessment or give kids some practice opportunities, those would be there. And then lastly, if you're looking for something more in the way of a formal worksheet, something that's already put together for you, there is one of these, again, they're just called worksheets for each module. And they're all set up the same. They start off with a matching bank. And then there's some multiple choice questions followed by a little true false question section. And then there's some short answer sections or questions here in this last section that are a little bit more challenging. And then the answer key follows. And then there's a short rubric here if you want to use that to grade your short answer questions. So anyway, those are the teacher materials that we have built so far for the modules that are posted online. So any questions, or Andy, is there anything else you want me to share?
No, that's great. Although I see a course distillation tab. Is that for us to see, or is that just a worksheet for you?
Nope, I have it started.
Okay.
And so I have gone through and we just divided this. We were following another model, electrical, mechanical, engineering, and then computer science. So pulled out the skills or the concepts that fit into each category. If you're looking for something specific, you can see what skills or concepts fall into each.
This is cool. I haven't seen this yet. Nice. I'll be looking. I'm sorry?
I said, I think maybe Stephanie has it, but I'm not positive.
Yeah, she didn't tell me about
Maybe I haven't shared it with her yet.
I have not seen this one yet.
Oh, okay.
Oh.
I am here. This is
It is
fantastic.
just my own little, it's my own little secret then, I guess.
I'm looking forward to it though.
Okay, very
And
good. Yeah.
yeah, as you can see, she's put tons of work into these and they're just beautiful. I give them a final check and I put them up on the private area of our Educator's website.
Which I'll be talking about next.
Yep. And I do have the worksheet for each of the 5 tutorials specific to this kit already posted. I have put up a teacher's guide and test bank for the Servo chapter you were working on today, and I'm working my way backwards. There's a few questions I have for Nicole and spots here and there that we haven't quite worked out, which is why I'm working back instead of forward through that list. And as you can see, she still has wonderful things she has in process that we will be adding as those become available. And Andy will be talking about how to have access to these materials very soon. And I just wanted to put out there, anyone who I sent an email to yesterday saying that you have a new account made for you, but did not get the automated email from our system, please check your spam folder. And if it didn't show up there, it may be that your district is blocking this domain. And if that's the case, I'd be happy to use the alternative email address you provided on the Educator's course application to set up an account for you that will just bypass that. So just shoot me an email directly or to education@parallax.com and I'll take care of it for you. And that's it for me. So I'm going to mute myself again.
Okay, and then I'm gonna take us to, let's see if I share my screen. Do you mind if I end your screen share, Nicole? Hello? You're
Good.
muted.
Yeah, but I was on mute. No, go ahead, Andy.
Okay, and by the way, let's all have, let's see, so I'll share my screen. Screen 2. And let's quickly all put our hands up and clap for Nicole. Thank you for visiting us today. That was excellent. All righty. And then I am looking for my slideshow. Okay. Yeah, I'll get back to the servo measurements after we talk about the educational resources. So they are all at learn.parallax.com. Let's see here. I'll paste that in. So it's learn.parallax.com/educators. And I just pasted that into the chat. Now, when you get here, there's basically educator resources for all of our different robots and electronics kits and etc. And so the link I just followed is the What's a Microcontroller with Python one. And just pasted that in. So the way we have this set up is that anything that can be publicly available is publicly available. And the only thing we hold back is the assessment materials. Although, yeah, the teacher guide, we'll have to take a look. I can't remember if the teacher guide has solutions in it. I think it does. And so, Nicole, I think we want to keep the teacher guide in the educator only access, but we can figure that out. And at any rate, so some examples is, obviously we have the Cyberscope linked, we have the tutorials linked, then where to buy the online editor. So these are things that are public. There's also a general teaching strategy guide. And this is where Stephanie mentioned that she's in the process of posting things. And so we'll see more here in the public downloads as well as the private downloads as resources become available. Then there's the assessment materials. And so that's what you'd want to log into. So this was the email that Stephanie mentioned where you're getting a learn.parallax.com account. And let's see here. So now going back to all right, so here we are. So you might not get some of this editing stuff that I have. But now here are the educator downloads and assessment materials. And so, so let's see. So Nicole or Stephanie mentioned that she posted the Servo material. So here is the teacher's guide that Nicole worked on. I'm downloading these, the test bank, the worksheet. Yeah, so there's, so then if we go and look at our downloads, so here's the test bank, a Microsoft Word document. And so here are
think we lost him.
I think maybe we did. I can explain what we're looking at though. You can still see Andy's screen. You're looking through an extra set of materials of the questions, exercises, and projects organized by the individual lessons in the tutorial. Oh, we've lost his screen as well now too. So here, let me see if I can get there.
I think it may take Andy a minute to get back. When he
Yep.
said that the oscilloscope that he was going to show sometimes his computer crashed with that. So maybe it did happen.
Can I ask a question about the oscilloscope?
Sure.
So I was talking to the physics teacher yesterday, of course, well, actually Tuesday, all excited about when I came, back from Monday's session. He was wondering if the oscilloscope works with sound waves or just the electrical waves.
The oscilloscope is getting data from the microbit itself. And so I don't know that it's going to be doing anything other than getting the electrical information from it. It's a virtual scope. Andy can probably explain better. We can see the signals that we're using to generate things, but I don't think we're going to be able to measure anything that isn't connected.
So my question and his question was, can we add a speaker to the breadboard and would it pick it up there? Like, is there a small speaker that you can add, then it would allow for the capture of sound waves?
The microbit 2 should have a speaker included in the actual device. So could be fun to test it out.
The 2.0 microbits to the 1.5 microbits don't, I believe, and I'm not sure whether his underlying modules are cooperating with the speakers at this point. This is a good thing to ask Andy about if he can get back on. And I'm also taking some notes for some follow-up questions and after the fact, because he's the expert on that.
So Andy confirms that he got the blue screen. So he's trying to restart now. It will take him about 3-4 minutes to get back in.
Yeah, we're looking at starting, not this next school year, but the year after, between me, the tech department, because I teach computer science, he's the physics teacher, and the tech department to try and add a electrical course. And so I thought, well, there was a lot of nice online free resources that you're offering, as well as, how to integrate certainly the products and stuff. And so that was just one of his questions as we're thinking about, that program, and that's something he would want to add. So I was just curious about that.
But that is a really good question, a really good idea. I'm sure Andy can give you a little more guidance on that. And if you end up experimenting along those lines, we'd love to hear about it. And like someone mentioned in the chat, the version 1.5 microbit and the 2.0 are different in that the speaker and microphone options that are on board. Right now, all the lessons we have are compatible with both versions, and we'll may need to differentiate in the future if there are some activities that are only going to work for one model or the other.
Hey, Stephanie, I see a couple people are leaving, and since we have a minute, I just wanted to tell everybody that I put together a Google Doc with all of the links that Andy's been giving out. I ended up with like all these tabs on my screen. So I just shared the link to that Google Doc in the chat. If anybody else is interested in it, it helps me keep my stuff organized in folders in Google Drive. So I just shared that with everybody.
Thank you so
Yes.
much for doing that. And I really
you,
appreciate
Jennifer.
some of those. I am going to be adding some of those links to the product page for the kit that you received, and also for the educators page on the Learn site, where I also have an accumulation of links. Most of them are already there covered, but not as directly as you have them. And that would be a really good place also to add back the little buttons to the videos that we're taking today. So I super appreciate you doing that.
Yes, and also we are posting the videos, the recordings of all these Zoom meetings. And we try to put in the comments of the video, we try to paste there all these links. The problem is YouTube doesn't allow us to do URLs. So you need to copy and paste the links. They don't work. So actually in a Google Doc, it could be much more efficient too. So you could actually click on the links.
Can I ask if we're going to get any documentation that we've completed this course that I could submit to my school?
Yes, I can create a certificate for you. I do this on request, not for everyone who doesn't necessarily, I don't make them automatically for everyone who enrolls, but definitely just email me at education and cite this class, and I'll be happy to provide those.
Yeah, and if you, you can actually, oh yeah, that's right. Everybody has Stephanie's email because that's where the learn.parallax.com sign up came from. So just reply to her on that thread, I guess.
Sure. And we had, while you were gone, while you were away, we had a fascinating question about what you might be able to do for detecting sound waves with the microbit microphone and speaker, and have that be visible on the oscilloscope for maybe some physics experiments. Nancy was asking about that, as her different departments for technology and computer science and physics are looking on how to maybe each pull something out of an electronics course.
Okay. Yeah, that's an interesting question. I think that it's going to be difficult to use the microphone to actually record a waveform. So if we were to speak to that microphone, I do not think it's going to be able to record and display enough data points to show the waveform that would be our voice. But let me see if I can get to
Andy, if you, in the case you generate the sound with the microbit, then you can display everything, right?
Exactly. Yeah, because what we do is if we're generating a sound, we could send the data that represents that sound. It would not be a measurement of the sound per se, but it would be, it would represent and match the sound that the microbit is generating. And I can show you an example of that. Share screen. Okay, so going back to learn.parallax.com, and it's basically to finish off the idea of the servo measurements that we didn't quite get through, and sorry about that. So as we look at these servo measurements here, the microbit is also not fast enough to sample a bunch of data points to show us on the oscilloscope screen pulses that are happening as briefly as this one is. But we do use the microbit to measure how long that high signal lasted. And then the script actually sends points that represent that high signal and the low signal following it to the Cyberscope. And so by doing that, we get a pretty credible measurement oscilloscope wise for the signal that the microbit is being sent to the servo. And so what Aristidez is saying is essentially, well, if you're sending a sound of a certain frequency, what could be done, and the more I think about it, the more I want to do it this way, is so here is an example where the Cyberscope is plotting a sine wave and an exponential decay wave. And I think you saw this when you were doing the homework before the first day. So basically, if we know that we're sending a sound wave of thus and such a frequency, we can graph, we can tell the microbit can essentially make a list of points and send them to the Cyberscope to make a graph that corresponds with that frequency. So that's what I will try to do.
Yeah, it's just something that, you know, when I went back saying, hey, this was really cool, you know, I know we're looking to do this, you know, create this course. And so just trying to think, is it something that, you know, is it going to be enough, you know, what you already offer? And maybe till we get there, things will change as well. They always are. So.
Well, yeah. So there's more material that's in progress, but I've taken a little bit of a break thanks to the supply chain crises that have been going on. If you think about the kits that you received, they have quite a few parts, and if we have difficulty getting even one of those parts, it makes us unable to ship any of the kits. And so, so there's been a lot of work that we've been doing to make sure that everybody can still get kits when they need them. And I'm hoping this eases up in a while and I can continue to add chapters. In fact, if I can get back to I'll share my screen again just to show you what's on what is planned. And let's see here. Okay, I'm going to go off screen for a second to bring up the slideshow. I had a nice, robust blue screen of death that caused me to disappear. From the workshop. And what I wanted to show you was near the bottom, I believe. Yes. So here we go. So this is the plan. So that these ones here that are live links are all published. And we went through at some level of detail all of these guys today. And then I'm in the middle of the potentiometer one right now and was planning on doing some of the potentiometer activities where you twist the potentiometer and the servo turns and so on. I can share out the document that has the code examples if you'd like to try that later. And then, so that's coming up next. And then we've got a 3-color LED, light sensor, infrared detector, and then essentially AC signals is part of music and tones. And then more about signals with the analog to digital converter. I doubt that we'll get to this, but eventually I'd love to publish something that shows how to use a filter to, take a sine wave and make it kind of go away if it's outside of what the filter is filtering for, and make it full strength if it's inside what the filter is filtering for. You actually have the parts for that in the kit. And then more inside how the multimeter that you'll have been using the whole time works. And we actually did the accelerometer servo control. So I can kind of remove this because it ended up being inside the servo chapter. So that's what's planned. I don't know how far I can get, but certainly I'm going to, as soon as all supply chain things have been worked out as far as the thing I have to do, which is, take a look at the parts and make sure from the engineering standpoint that they are okay for the kit. Once I've got all those solved, my plan is to get back to writing and starting with the potentiometer.
Can you tell me if you have any workshops planned for the spring with different topics like this one?
Okay, so we have not started planning the spring workshops yet, but we do regularly do workshops. The most common ones lately have been this one and the Cyberbot. And but in the recent past, we've also done the activity bot, the Arduino, the BOE Shield bot with the Arduino, which is similar to the Cyberbot, just has an Arduino instead of a microbit on it. The Cyberbot has the microbit. And so yeah, we regularly do workshops. I also hope to be doing another workshop that's like this one, but hopefully visiting more topics as I add to them here in the table of contents, which is actually going to be right. So they'll all appear right here when they're ready. And so we'll
advertise the events, because I got mine because I went to the Discovery Forum in June, and that's when Ken was one of the guys there and advertised this, and I signed up for it through that.
Mm-hmm. Well, now that you are now that you signed up for learn.parallax.com, one of the things that you will get in your email is an announcement when we schedule courses. And then every few weeks, Ken, who you met at the Discovery Forum, will share out, some kind of interesting email about things that are going on. And today's was actually kind of neat. I'm going to bring it up and share it with you. Am I still sharing the screen or no?
Nope.
Okay.
And also, for example, cyber.org, once we publish those classes, they also repost our classes on their website. So there are several ways to find out our classes.
Yeah, so what I was saying was that this is, so when I was talking about all the different things that we had planned, could you not see that? Or could you guys see this lesson?
Yeah, we
roadmap?
saw that.
Okay, good. And then, but you didn't see when I just called this up and said, hey, they'll be appearing here.
Yes, we could see that too.
Oh, good. I don't know how I accidentally hit the, unshare the screen button. I am looking for the email from Ken that came today.
Mine was stating a 10% discount, and I just ordered materials 3 days ago. But I think it was on some fun packs or whatever. Bundle packs.
Okay, so here we go. So this is an email that, yeah, so we're having our holiday sale. So of course, that was the first thing Ken mentioned, is that there's a discount on various kits. And then he introduces staff, and we've all decided that we think this picture is just the best. This is our lead manufacturing technician, Terrell, and he was inside the selective solder machine cleaning it out. And so it looks like we store him in there when he's not at work. And so yeah, these emails come out once every week or two. And in here you will see, hopefully fairly soon, an announcement of upcoming courses. Okay, well, any other topics or questions?
Yeah, Andy, I have a quick question on your cybersecurity lesson roadmap.
Okay.
I think I see that a lot of those lessons are connected to your Cyberbot, but I'm looking at the one at the end, the encryption intro.
Mhm.
Do you need the Cyberbot for that one?
No, as a matter of fact, let's see, I'll do a follow-up item. I'll send you a list of all the different Cyberbot lessons that you can actually do with just a microbit, which means you'd be able to do it with this particular kit. Need to remember to screen share here. Okay, share screen.
I just got done using one of the cyber.org units, and I think that would go right along with it.
Yes, I agree. So that's going to be back a little ways here. So back at learn.parallax.com under the Cyberbot. All these prerequisites are doable with just your microbit. Lots of good lessons here too. There's real basics like the one you guys all did to start out with, which was the writing microbit programs. We did some excerpts from there. Computer microbit talk is a good one. And then for more computer science intensive topics, we have some of these which end up coming into play later during the cybersecurity part, understanding dictionaries, exceptions, and strings. So then here's the main Cyberbot stuff. But once we get to the encryption intro, these guys are all microbit only for the most part. There's a couple of places where they refer you to and tilt control is mostly microbit only. It's only after going through a lot of tilt control material, like talking about the Z-axis on the microbit, and earlier on talking about, how you can rotate it and, from the X and Y sensing axes, calculate the angle. So there's lots of good material in here that actually the Servo chapter refers you to here before getting started on it as an optional thing to understand and learn more about the accelerometer. Then, so that's it. I think those are, so it's these cybersecurity chapters. Oh, and then the radio basics and radio data are also microbit only. So you can do those with this kit, as in, with just a microbit or the what's a microcontroller kit, and then everything in prereqs.
And can you show me, Andy, how do you go back one page?
Okay, so this is learn.parallax.com.
Okay, so that's on the main page there.
Yes, and
Okay.
then under Python, you've got Cyberbot and what's a microcontroller. And so what's a microcontroller is these guys that we've been going through. And then Cyberbot has lots of additional stuff, and I'll send you a list of these links that can all be done either just with your microbit or mostly with your microbit. And you might skip just a few activities within it, like the tilt control of the Cyberbot. You can do lots of tilt experiments and just skip the part where the Cyberbot comes in.
Thank you.
Certainly. Yeah, okay. And for the participants, we are down to one screen's worth. So I can see you all now. I'm more than happy to stay for any additional questions or comments until we're all done. And you have a great weekend too, Edward. Just saw Goodbye chat from him. Thank you, Jennifer. Looking forward to seeing you again in another one. Cool. Anything, you got any other good jokes, Cheryl?
No, by yourself is the best one.
Okay, tell that one for Stephanie's benefit, if you would.
Oh, well, okay, so Stephanie, do you know what the most lonesome bayou in Louisiana is?
I guess we'll have to.
No, I don't know.
By yourself.
Oh, no.
Now, Chuck at cyber.org loves to tell those during his trainings.
I've told Chuck and I presented together at our summit, and I told him that joke.
Oh, well,
Yeah.
I'm sure it's being retold now like crazy. Both Chuck and then Kevin Knowlton also loves
Yes.
a good dad joke.
I actually told Kevin Knowlton that joke a couple of weeks ago at CSEDCon.
Uh-huh.
Yeah.
You made his day.
Yeah, he laughed. He thought it was good. I take liberties though, because my mother's family is from the Lake Arthur Jennings area in Louisiana, so I'm a Cajun girl.
Ah, I see. Yeah. Yeah. One of the things that Tommy told me was that given the rivalry between Texas and Louisiana, that you know, you never want to guess that somebody's from Texas might be from Louisiana and say, "Hey, are you from Louisiana?" It's like, what are you saying? All right, folks. Well, how about if we, it's good to see you and thank you again.
Bye.
Bye-bye. Paul, anything before I shut the meeting down? Well, I will take silence as assent to end the meeting. So I'm going to stop recording first.